Welcome back to Chemistry in the Physical Setting. This is Unit 1, Atomic Concepts, and Lesson 2, Atomic Structures. And last lesson we dealt with atomic theories, and that the structure of the atom consists of a nucleus with an overall positive charge surrounded by negatively charged electrons. In this lesson we'll dive deeper into that and talk about the subatomic particles contained within the nucleus, as well as the electrons surrounding the nucleus and the orbitals. And we'll talk about their energies, their charges, and their masses. If you remember from the last lesson, Atomic Theories, the structure of the atom consists of a positive center that contains most of the atom's mass, and this is called the nucleus. And this nucleus is surrounded by a negative electron cloud known as an orbital. And so we'll begin by talking about the subatomic particles contained within the nucleus and contained within the orbital. And we'll begin with the nucleus. Okay, so again, a nucleus is a dense positively charged center of the atom. And in the nucleus, two types of particles can exist. Protons, which have a positive charge, and neutrons, which are neutral, meaning they have no charge. And so if we're looking at the nucleus of a hydrogen 2 atom, that nucleus would contain one proton, which is positively charged, and one neutron, which has a neutral charge, which essentially is 0. Of the two subatomic particles contained within the nucleus, or nucleons, we'll begin with the proton. Okay, and so the proton has a mass of 1.67 times 10 to the negative 24 grams. Which is like saying 0.2300167, so extremely small number. In fact, that number is so small that it's very inconvenient to use, so a unit was actually developed when talking about subatomic particles, and that unit is the atomic mass unit. And so it's more common to just say that the proton has an atomic mass unit of 1. So 1 proton equals 1 atomic mass unit. Okay, and so it also has a positive charge, which we just said previously. So protons have a positive charge and a mass of 1 atomic mass unit. And so each atom of the same element must contain the same number of protons as every other atom of that element. So for instance, hydrogen 2 is hydrogen due to the fact that it has 1 proton. And if it had more protons than 1, then it would no longer be hydrogen, it would be a different element. Okay, and so the number of protons in the nucleus of an atom is the atomic number of that element. So for instance, hydrogen, if you look on the periodic table, will have an atomic number of 1 because it contains 1 proton. And so if you were to add another proton to this nucleus, then it would have an atomic number of 2. It would no longer be hydrogen, and it would be the element helium. Okay, so hydrogen, this is what hydrogen would look like on the periodic table of elements. And that number right there is the atomic number. And again, it is 1 because hydrogen, again, has 1 proton. The other subatomic particle contained within the nucleus is the neutron. The neutron has a mass approximately the same as the mass of a proton, which is 1 atomic mass unit. They're slightly different in mass, but the difference is so small we just consider both to have a mass of 1 atomic mass unit. Okay, and again, since a neutron is neutral, it has essentially no charge, so it's neither positive nor negative. And so atoms of the same element can contain different numbers of neutrons, whereas if we change the number of protons previously, we would then have to change the identity of the atom. But in the case with neutrons, adding or subtracting neutrons from a nucleus doesn't inherently change the identity of the atom. So adding another neutron to a hydrogen 2 atom would still be hydrogen. It would just now be hydrogen 3 with a mass number of 3. And so the number of neutrons in an atom can be calculated by subtracting the atomic number, which is the number of protons, from the mass number, which is the sum of both the protons and the neutrons. So if you look at the example I have on the screen here, hydrogen 2 has a mass number of 2. and hydrogen has an atomic number of 1 because it contains 1 proton. So 2 minus 1 equals 1, which means we have 1 neutron. If we were to look at another atom of hydrogen with a different number of neutrons, like hydrogen 3, we'd see that now it has a mass, this hydrogen atom has a mass number of 3. And so again, we take the mass number, which is 3, subtract the number of protons, or the atomic number, which is 1, and we'll end up with 2, meaning that this atom has 2 neutrons contained within its nucleus. And again, adding a neutron here does not change the identity of the atom. The atom is still hydrogen regardless of the fact that now it has 1 more neutron. Whereas if we change the number of protons in this atom, we would then change the identity of the atom. Now we've discussed both the subatomic particles contained within the nucleus, which is the positive proton and then the neutral neutron. Now let's consider the subatomic particles contained outside the nucleus in the orbital. And so an orbital is a region of space outside the nucleus that is the most probable location of electrons. So electrons are not contained within the nucleus, but outside in this electron cloud that we call an orbital. So the electron has a mass of 1/1836th the mass of a proton, and that's so small we just consider it negligible. We just figure that it's close enough to 0 where we don't need to add it to any calculations, and that the charge of an electron is opposite of a proton but equal in magnitude. So an electron's charge is -1 where a proton's is +1. And so these charges end up canceling each other out, and the entire atom then is neutral. Okay, and then its mass again is so small we just consider it to be 0. So if we were to look at it as a decimal, the mass of an electron in atomic mass units would be 0.000547 atomic mass units. And again, this is so small that when doing any calculations, we just approximate the mass of an electron as being 0, and we don't even worry about it. And so since an atom's overall charge is neutral, the number of the protons must equal the number of electrons. So since their charges are opposite but equal in magnitude, if you have 1 proton and the overall atom is neutral, that means you have to have only 1 electron to neutralize that positive charge. The location of electrons, however, is a little more complicated than describing location of a proton or neutron, because they're just contained within the nucleus. But an electron can occupy different orbitals depending on each electron's quantity of energy. So the greater the energy of an electron, the higher the energy level it will occupy. And each electron energy level has a limit to the amount of electrons that it can occupy. So if we're going to look at, let's say, a much larger atom like krypton-84, Krypton-84 has 36 protons because krypton has an atomic number of 36. And since it's Krypton-84, 84, which is the mass number, minus 36, which is the atomic number, will give us 48, which is the number of neutrons contained within the nucleus. Now the electrons, however, are a little more complicated. The first energy level of an atom can contain 2 electrons. So of the 36 electrons that this atom must contain, 2 of them can be contained within this first principal energy level. The next energy level can hold a maximum of 8 electrons. So now of the 10 total electrons that we've discussed so far, 2 are within the first energy level, 8 are within the second energy level. Okay, and we still need another 26 that are unaccounted for. In the third energy level, we have 18 electrons, which is the maximum number that can be contained within that energy level. And the final energy level is not completely filled. For krypton, there's only 8 electrons in the outer energy level. 32 electrons can occupy this energy level, and that's basically about as high as it goes. But the important factor here is that only 2 electrons can be contained within the first energy level, 8 within the second, and 18 electrons within the third. And the further out from the nucleus you get, the greater the energy. So when comparing the energy of an electron in the first energy level to an electron, let's say the third energy level, the electron in the third energy level has a much higher amount of energy. Even though their mass and their charge are essentially the same, the electron in the third energy level has a much higher energy. Okay, and so to summarize today's lesson, if we were to look at the three subatomic particles contained within the atom, we have their symbols, which represent what they are, and then their charges. So a proton has a charge of +1, a neutron essentially has 0 charge, an electron has a negative charge. And the mass of a proton is 1 atomic mass unit. The neutron is also 1 atomic mass unit, and the electron has a mass that is again so small we can just consider it to be 0. So we do not have to actually memorize this number. Just when we're calculating the mass of an atom, we can leave out the mass of an electron because it's so small it won't affect the overall mass of the atom. And then the locations of all three subatomic particles, both the proton and the neutron, are contained within the nucleus, and then the electrons are contained in orbitals outside the nucleus. And so a quick example to just again summarize what we did. If we were to draw the structure of the following atom, carbon-13, we would first need to know the number of protons. So if we look in the periodic table, we'll find that carbon has an atomic number of 6, which means that it would have 6 protons within the nucleus. Since it has 6 protons and it isn't a neutral atom, we can then assume that the number of electrons have to equal must equal the number of protons. So then we'll have 6 electrons. And again, 2 contained within the first energy level. That's the maximum amount of electrons that can be contained within that energy level. And then 4 in the second energy level. And again, we can put more electrons in this energy level, but carbon only has 6 electrons, and so we'll just stop there. And then finally, since carbon-13 has a mass number of 13, we take the mass number and subtract the atomic number, so 13 minus 6, and we end up with 7, which is the number of neutrons contained within the nucleus. And so we can do this with any atom. Whenever we have the mass number and atomic number, we know it's an atom, we can then determine the quantity and region of all the subatomic particles contained within that atom. So stay tuned for next week when we'll discuss isotopes, and hope to see you in class tomorrow.